I'll turn it over to today's presenter, Sid Choudhury, Senior Vice President of Product at Yugabyte.
Thanks, Michelle. Hello, everybody. A very warm welcome. Good morning, good afternoon, wherever you are. Excited that you have joined us today to listen to this talk, which is actually very exciting and is close to the hearts of all of us here at Yugabyte, because it's what differentiates us and the distributed SQL database technology gamut from the legacy traditional relational database technology that we have all been using in the past. So before I go into geo-distributed SQL, I want to lay down some map on the ground that to highlight the categories of databases that we have come to know about and the sort of clear distinction between them. And those two categories are OLAP and OLTP. OLAP stands for Online App Analytics Processing, and OLTP stands for Online Transaction Processing. They are not the same. However, anybody tells you that a single database does OLAP and OLTP, that is just not true, because they're fundamentally different architectural paradigms. If OLAP is about writing once or very infrequently at night and read frequently with lots of different kinds of queries, OLTP is both read and write frequently at the same time. OLAP is about few concurrent sessions. As a result, and the data is not changing. So weak asset guarantees are essentially the name of the game when it comes to OLAP databases, versus OLTP databases cannot do weak asset guarantees. They have to support many concurrent transactions, which means the isolation level, which is the fundamental aspect of an asset database, has to be at the strictest level possible, which typically is serializable isolation. OLAP databases are long-running ad hoc queries, versus OLTP is about blazing fast, well-known queries. And as a result, the ad hoc queries has the potential to scan entirety of large tables with potentially billions of rows, versus OLTP is about user-facing applications that need to do point reads and short-range scans for that particular user or a collection of users in a single department and so on. And the sum total of all of this is that OLAP databases typically are about petabyte scale data storage across multiple nodes, versus OLTP databases are typically about terabyte scale data storage. Again, it depends on whether it requires multiple nodes or not. So with that, I want to highlight that today's focus will be on OLTP databases and not OLAP databases. So now that we have established the difference between OLAP and OLTP, what is distributed SQL? Why is there so much excitement about it? We keep hearing about it. And here at Yugabyte, we have built an entire company around that architecture. So distributed SQL is essentially a revolutionary OLTP database architecture. Why is it revolutionary? Well, relations and asset transactions and SQL data modeling are given. They have been around for 40 years, more or less. But what is new is they have not been brought to bear in the form factor that highlights the remaining three attributes, which is ultra resilience, ability to natively and automatically tolerate infrastructure failures resulting from disk corruption or node failure or zone failure, region failure, cloud failure. All of these sort of failures of, also in distributed system terminology known as network partitions, they all are name of the game. They're very common in the modern commodity shared nothing cloud architectures that we leverage today, whether it's Amazon, whether it's Google, Azure, does not matter. And also Kubernetes, for example, is very much on that failure prone technology. Secondly, it's about ability to scale horizontally and as big a cluster as possible, so that if you have a application that is phenomenally successful and it needs to store large amounts of transactional data and serve them at ease, then you have the ability to draw throughput essentially at the end of the day, both write throughput and read throughput by simply adding new nodes into the cluster. Last but not the least, which is the focus of today's topic, is geo-distribution, ability to take a single cluster and essentially spread its nodes across multiple regions or multiple data centers that are geographically far apart from each other, and as a result get the ability to do two things. The first one is obvious, its ability to tolerate the region failure and automatically fail over to some other region. Secondly, it's about bringing data closer to the geo-distributed users so that the user experience remains extremely low latency. Okay, and this is the focus for today's talk. We'll drill a lot into this and figure out what are the various smart techniques we can deploy to just draw maximum mileage out of this geo-distributed deployment topology. Now, when you combine these three attributes with SQL, relations, and ACID transaction, that's when revolution happens. Now, why do we care? We do care because databases haven't kept up to the needs of the two consumers that databases, I would say, serve. One is the microservices applications, which need the ability of SQL to essentially model data once and change queries as and when needed with high degree of consistency, ACID transactions, and relations, which help us, normalize data and change queries on demand. And also, the scalability aspect of microservices becomes important. Second aspect is the multi-cloud infrastructure that is now available at our fingertips. We're no longer in the era that we live in private data, our applications live in private data centers or co-located data centers where hardware has to be hauled in every time we want to deploy an application. Today, compute, storage, and network is literally at our fingertips with the click of a button or call of an API across, at the very minimum, the three major cloud providers. So how do we exploit that infrastructure to deploy fast and deploy across the globe while tolerating all kinds of crazy failures that are coming our way? Because it's those that hardware infrastructure is not necessarily built with the same tender love and care that we are used to in on-premises data centers. So if you take the sum total of that, then you need distributed SQL because it provides the developer agility, build with relations and ACID transactions and build horizontally scalable microservices. It gives us the operational efficiency to deploy on any cloud, any Kubernetes infrastructure. And then end result is that businesses can deploy applications, release new services faster than ever before. So it is a foundationally important change that we are seeing in the application development market. Now let's go into distributed SQL architecture. It's different than our typical monolithic RDBMS like the Oracle, SQL Server, Postgres, and so on. They have only one node where writes can be sent. You can have read replicas as standbys, but writes can only be taken at one node, and that is fundamentally different in distributed SQL, where minimum you need 3 nodes because at the end of it, the replication underlying of data is happening using distributed consensus protocols called like Raft and Paxos, which require an odd number of replicas in order to tolerate split brain or network partition scenarios. And in those 3 nodes, every node can take writes for some subset of the data. And for example, if let's say these subsets are called shards, right? We take a table, we deploy various kinds of sharding mechanisms, hash sharding, range sharding, and then we distribute those shards across multiple nodes. Each shard has a shard leader on node 1, which is the fault domain 1, and it has 2 more shard followers in other fault domains, in 2 independent fault domains, and in this case, 2 different nodes. And that is the key here. The way to make this OLTP data so agile is by taking this large problem and then breaking down into small distributed systems, each one being a Raft group or a Praxis group. And then as nodes keep adding or getting removed, we keep on changing only a subset of these distributed systems, not every shard in the system. That gives enormous power for us to change our clusters as and when we demand. And as far as the development team is concerned, they are still speaking the standard SQL dialect, and they are actually abstracted away from how many nodes and how many shards are actually participating in this cluster, because to them and the microservices they develop, there is only a single logical relational database. A very powerful concept. This did not exist till a few years back, before geo-distributed databases like Spanner were introduced. Google Spanner were introduced to the world via the research papers from Google. So what is Yugabyte DB, right? And why are we excited about distributed SQL? So we are a Postgres compatible. So the SQL dialect that we support is Postgres. And the wire protocol, which is essentially the transport mechanism on using which the dialect actually gets passed on from the client driver to the database cluster, is also Postgres wire compatible. And that allows us to go serve a lot more wider variety of applications that are out there, instead of us coming up with a net new language of our own. That's one. Secondly, it's high performance. We've built ground up in C, C++. Actually, we reuse the native Postgres query layer as is, and that allows us to provide a higher level of performance, which is both lower latency and higher throughput than you typically see in distributed databases. We're fully open source, 100% Apache 2.0 open source, and we've taken a very aggressive and sort of against the grain stance where the database is fully open source and we commercialize purely on the management platform. Very different than other vendors who either do fake open source through licenses like BSL, or they actually, the entire goal is to upsell you to a different enterprise edition, which has some features that you cannot live without, like backups and restore and encryption and so on. Last but not the least, we are fully cloud native. We are built in the era where Kubernetes is the default IaaS substrate. As a result, we run natively inside Kubernetes as stateful sets. We offer Helm charts, we offer operators, and we integrate deeply into the cloud native ecosystem, like with the likes of Prometheus, for example, where every layer of the database actually exposes metrics in Prometheus format natively. The end goal is the database becomes very easy to orchestrate, manage, observe, and sort of remain resilient to failures and change as time passes, right? So that is what Yugabyte DB is. And obviously it is a fully distributed SQL database that follows the architecture of per shard distributed consensus that we talked about. Additionally, it also does fully distributed asset transactions on top of this distributed consensus layer by using a variation of a two-phase commit protocol for multi-shard asset transactions. Okay, so now this is the lay of the land. Distributed SQL is the future of the RDBMS. Monolithic SQL has reigned for supreme, I would say, for 40 years. But slowly the world is moving towards cloud, and cloud gives us the opportunity to horizontally scale and also run on heterogeneous infrastructure. And as a result, that infrastructure can fail often. Hence the designs of Spanner and Aurora from the two big cloud providers. What we have done at Yugabyte is essentially take the best parts of both the database architectures, Postgres compatibility like Aurora at the top, and a Spanner like distributed document store at the bottom, that allows us to serve various kinds of transactional workloads with ease. Now, let's go into the core topic, which is geo-distribution and relational databases. Before I talk about distributed SQL, how does geo-distribution work in today's world that we have seen in the past, right? So imagine you have a multi-region microservice where region one is running the same microservice and same set of microservices, and the region 2 is serving the same set of microservices. If there is a common metadata store that microservice relies on, then it is inherently running in only one region. And in this case, that is the active master, and I have used Postgres just to make it concrete. So region 1 will experience low latency reads and writes, but region 2 will experience high latency in this kind of a form factor. And we use asynchronous replication to create a passive replica in a separate region, so that if disaster strikes to region 1, then the passive replica can take over, albeit manually, and some amount of data loss will happen because the commits that have not flowed yet to the passive replica will be lost for some time. So this is what we have been dealing with, right? You can enhance this architecture a little bit more, where instead of having all the writes go to only one region, you can have two masters, which is full copy of data on both sides, both the regions, and then doing bidirectional async replication using a simple conflict resolution protocol called like last writer wins. But the challenge here is that if the same record is being updated on both sides in the application that you are building, then you are guaranteed to lose one write. There's no denying of that fact. And that data loss may not be acceptable for things that are getting shared across the two regions. For example, the reason why Spanner was created is because last writer wins was not good enough when trying to decrement AdWords credits at Google, right? Because we cannot lose, Google cannot lose the AdWords credit of the marketing team in EMEA region just because the marketing team in North America also did a decrement of the AdWords credit, right? So, and that, which means these kind of architectures do not have globally consistent reads, right? That's at the heart of the challenge. So distributed SQL goes after these, the limitations of these two topologies that we saw by taking them head on. So the first simplest way to deploy distributed SQL is to deploy in a single region, but multi-zone, which means that you will have at least one node in each availability zone, but it's a single region or a single data center, and zones can be thought of as racks. And in this case, your data is consistent across zones, but and there is no write, cross-region write latency, but there is no automatic region failover or repair, because if this region dies, you have to recreate the cluster using previously created backups. There is no other choice. A step forward is single cloud multi-region, where you take a single cloud like Amazon or Google or Azure, and you say, I'll pick 3 regions and I'll run one node minimum in each of these regions. And this is where it gets very interesting and exciting, because now it is consistent across regions. When you do a write in one, let's say region 2, it will be immediately available in region 1 and region 3. And there is cross-region latency because laws of physics apply. In case of the distributed consensus protocols, you have to commit at minimum of 2 of these 3 places, the 3 replicas that are stored. So there is no escaping the cross-region latency easily. But the benefit is that you automatically tolerate region failures. Let's say region 3 died, then region 1 and region 2 will automatically heal by recreating the lost shard leaders in their own regions, and writes can continue to those shard leaders after like a couple of seconds. And so that's the real benefit of this kind of an architecture. Even I would say step forward is multi-cloud, multi-region, where a single app runs across multiple clouds, and instead of picking regions from the same cloud, you are now picking regions from the 3 clouds. In a way, this has the very similar characteristics of the multi-region deployment, but now the cloud themselves can throw some challenges. So this is a emerging deployment. Some users are supremely scared and they want to I would say, distribute their bets across multiple cloud providers, and that for a single app, and that's how they do it. Or the more common deployment is for a given app, you take a single cloud and deploy it in multiple regions. It can, as different apps get onboarded, they can pick their best of the breed cloud for that purpose. So that's another possibility. So with these topologies, it's clear that the second and third topology will have cross-region latency during the write path. So what can we do to sort of tackle this cross-region latency challenge that is in front of us? And that's what the remaining 9 techniques I'll touch on. So I've divided these techniques into 2 building blocks or 2 categories. One is the basic building block, where most of the time your application doesn't have to do any changes. It's that's the beauty of distributed SQL is it comes to you and without any schema modeling or any sort of intrusive changes to your application, you start benefiting from the basic building blocks. You can notch it up one level higher, where if you take a little bit more care during application development, you can draw even more mileage out of the cluster, and that's where the advanced configurations sit. So with that, let's dive right into the basic building blocks. So first is strongly consistent reads without quorum. Now the way it works is in distributed consensus-based writes. The hard work of committing the data at 2 of 3 places is already happening on the write path, right? So, and that with concepts like leader leases, you are absolutely sure that for a given shard, there can be only one leader at any given point of time. The sum total of these 2 properties lets you go to the shard leader and ask for the absolutely strongly consistent data, and the leader can directly serve it off its own local data without consulting with any peers over the network. And if no network is involved, then obviously there is no cross-region latencies involved in the read path. The write path, there is still cross-region latency. Now, a classic example for this is a user's password authentication flow in a globally distributed SaaS application. So, and as you can imagine, the number of login or password authentication requests to that SaaS app are much more voluminous compared to the user changing the password, which is the write path. So it is actually a good trade-off, where if I am trying to log in to salesforce.com or zoom.us, then the shard leader immediately looks at the latest the current password and tells me whether this password matches what the user has entered without involving any network. As a result, it becomes blazing fast, right? So it is an important it's a built-in optimization that you leverage for a specific kind of application workload pattern. Taking that step taking that entire approach one step further, on the same node that is closest to the client, not only there are shard leaders, there are also some shard followers. And the shard followers are obviously not leaders, so which means that they have slightly stale data potentially, because some commits may not have reached them. But the good part is it's still timeline consistent. That means they're not out of order. They'll remain in order. And we can continue to ask that node to give us timeline consistent follower reads without again consulting any replicas which may be distributed over the network. Classic example here is I'm a retail product catalog, and each product has some user reviews or product reviews, and those reviews can be served by whatever node that is local to the client, right? Because if let's say there are really 1,000 reviews in the system, but my local client has only seen 998 of them, I can still serve those 998 without consulting the followers, the other 2 replicas in 2 other regions, the user experience, on the other hand, doesn't get degraded by the loss of those two latest reviews. User still feels that they have actually seen what they need to see, and the reviews are in order. So it's not like there is a poor experience that the reviews are sort of coming randomly at you. So this is actually a fair trade-off to do when we are building that kind of an ever-growing data set that that can leverage timeline consistency. So if we take number 1 and number 2 and we combine them together, now we can start serving entire complicated join queries of that single node with whatever data it has. So the shard leaders obviously have the strongly consistent data, and there are a bunch of followers in that particular region. And if we just rely on the follower reads and the strongly consistent leaders, and we power joins with them, then bingo, we have an ability to serve data from the local region without consulting any replicas. In an example workload here is, let's say, a list of tickets filed by a user who is again residing in that particular region in a help desk application. So I can immediately do a join, and I can see all the tickets that I had previously filed. And most likely, since the tickets were filed by me, most of even the shard leaders for the tickets will reside, high likelihood will reside in my local region. And even if, let's say, we're missing a ticket here or two, it will not degrade the user experience. 4, it's a variation of the number 1 technique, where instead of distributing the shard leaders equally among all regions, we pick a region where that actually serves most of our reads, and we make that region preferred for our shard leaders. So we tell the database that US East is the preferred region for all my leaders across all shards. And what will happen is the database is going to store all the leaders in that. And as a result, and this works only if the dominant amount of reads come from US East itself. And if that happens, then all I'm doing is doing, not just, serving point queries, I'm doing complete joins on the data on US East. And as a result, I am able to serve the app with low latency. A classic example on this is, let's say, we are building the loyalty app for Dunkin' Donuts, which is a US East Coast brand. We hardly see them here, even though I love them. Their loyalty app, imagine, is distributed like this across the country, but they can pin all the leaders in US East and have a great experience for their users for the normal path. And if, let's say, disaster ever strikes US East and that entire region goes away, the system still heals between US West and US Central, albeit all those users will experience a slightly higher latency because their queries will now have to travel farther geographically. Again, a fair compromise. Now we get into the more advanced configurations where there is a need to think a little bit more closely before even doing schema design. So let's start with row-level geo-partitioning. What if we could look at every incoming row and look at particular column in that row and say that if your column value, let's say country code, is North and South American countries, then I will place you in US East. If your column code is Europe, Middle East, and African countries, I will place you in Europe Central. And if your country code is all the Asian countries, I will place you in the Asia Pacific Japan region. What we have done is we've taken the entire globe and we have reduced them into 3 independent regions, and we have made the database essentially pin the shard leaders for those incoming data on those particular regions. The end result is that when reads come in from those users in those specific regions, for those users, the likelihood of consulting replicas for serving strongly consistent reads dramatically decreases, because I have already done the hard work at the right time, and I have ensured that my my local data for this region is already being leaded in the local region. And the example here is, let's say we're building the user profile app for Zoom, which is a massive globally distributed application at the core of it. And if we pin the users like this, the way I explained, then we rely on the user password authentication flow, which is the most common flow. All of us are logging in like 100 times during the day to Zoom. Those queries will be really, really fast by design, because if I am in Europe, then my query will never travel to US East for that data. So it's a powerful feature. Then comes what we call as a collection of techniques. It's co-located, co-partitioned, or interleaved tables. The entire proposition for this set of techniques is that related data, you store them as closely as possible. And close is essentially geographic proximity is the way to look at it. Co-located can be at the entire database level, where all the tables of a single database are co-located on a single shard. As a result, there is not even multi-shard communication. Forget about multi-region communication. Co-partitioned is you just traverse a parent-child tree and you pin them together in a single in a same, I would say, node, zone, or region or cloud. And interleaved, which is what the explanation shows here, and that's what Google Spanner uses, is you actually physically store the entire hierarchy of parent-child, is essentially foreign key style relationships, in the same shard, or in the same storage substrate. So in this case, we see that singer Mark Richards has 2 albums, Total Junk and Go Go Go, and his Go 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 album has 2 songs, 42 and Nothing Is the Same, right? So all of this data is actually stored together. So when a query comes in and it traverses the parent-child foreign key relationships, it's blazing fast. There is no cross-shard communication. There is no geo-distribution communication, right? Okay, now can we do something? I mean, we have looked at techniques that are all sort of happening on the server side. What can we do on the client side, right? So typically, even even with the server side getting distributed, if we are using standard SQL client drivers like Postgres or MySQL, then you don't have a choice but to go through a load balancer, because that load balancer is the one that will abstract out all these multiple nodes to the client driver. Remember, the client drivers don't know that there are multiple nodes. They were never written for the era of multi-node relational databases. So, but the challenge then kicks in that now I have to physically manage a load balancer, and I have to make sure that as I'm adding, removing nodes, I'm going and updating the load balancer list with that information. So it increases the operational burden. What if we could have topology-aware SQL client drivers, where we take the load balancer out of the equation? Each client driver directly communicates with the nodes of the cluster in such a way that it knows which shard is mapped at which node. And if new nodes are added and the shards get rebalanced, that also is communicated back to the client driver asynchronously. And as query comes in, the client driver just picks the right nodes and sends the query there. So there is no hopping around in the cluster to find the right location for a given node. And naturally, with this approach, since you're removing some hops between the client driver and the data, you are going to reduce the latency, and especially if the hops are actually across regions, right? Then comes the aspect of read replicas, and read replicas are not, I would say, they have been around for a long period of time. What is exciting in distributed SQL is that you can have a master cluster in region 1 where which is ready, which is taking the writes, and the write nodes are in the same region, but you can do unidirectional async replication out of this master cluster into a read replica cluster in a separate region. And that read replica has essentially timeline consistent data, albeit slightly stale than the followers in the master region. And it can serve reads blazing fast for the local clients. But if you send writes to the read replica, it will automatically redirect to the master cluster. So as an app, your work is very sort of minimal. All you have to do is, I want to talk to my local data center all the time, and if it and the database itself understands when to serve the reads directly off of the read replica, when the data is old enough that it now needs to consult the master, or when the data is actually a write request and now I have no choice but to send it to the master cluster. So all that intelligence is baked into the read replica altogether. As a result, your app looks very simple. Okay. Last but not the least, it's the classic multi-master deployments, which I touched on in the traditional RDBMS deployment. It's just that you had only one node to play with in each region, versus in this case, you can have, as big a cluster in each of these regions. And remember, the entire data set is present in both the regions, right? So you can have a 100 node cluster in another one and 50 node cluster in another one, but they hold the same data. And you can have bidirectional async replication. The data will be lost the conflicts will be resolved using last writer wins. But at the very minimum, you have the ability to architect your app in such a way that you deal with only part of the data in each of the region, and use the second region only as a failover region when disaster strikes. So this is I would say a very powerful paradigm, right? Which brings together sort of the knowledge from the traditional RDBMS era and marries with the advances in distributed SQL architecture, and allows you to sort of have a little bit of best of both the worlds, because writes will never experience cross-region latencies, and you will fail over to a different cluster only in under failures. So with that, I have reached the end. I would like to summarize by saying that distributed SQL is an exciting set of architectural paradigms, and it is the future of the RDBMS, because it brings together all the things that we love about the RDBMS and marries it together with all the things that we have traditionally loved from the NoSQL architectures, like native resilience, like horizontal write scaling, ability to do multiple different kinds of geo-distributed, hybrid, multi-cloud deployments. And the biggest value add for distributed SQL is you can deploy it any which way you like. There will still be a single logical SQL database as an application developer for you to interact with. Now, naturally, I think the concern is fair that geo-distributed SQL deployments can lead to cross-region latency, and they will if you don't put in any thought into it. But using the techniques that I highlighted in today's talk, you can actually work towards reducing cross-node and cross-region communication. Now, we divided the techniques into two categories: basic building blocks that leverage essentially the per-shard distributed consensus models, and advanced considerations where we do explicit data model changes, and we take more care in the application development, and even use newer smart drivers to ensure that we do not fall prey to the cross-region latency challenge. With that, thank you so much for attending today's talk. I recommend you install Yugabyte DB on your local laptop, on your cloud account, on Kubernetes, and provide us feedback and let us know your experience on Slack and GitHub. We're always there to help assist and move your application development and deployment journey forward. Thank you.
Thank you for joining today's webinar. We have a Q&A session starting right now. So if you have a question, look towards the bottom of your screen, click on the Q&A widget and type your question there. And Sid, we have 2 questions that have come in so far. The first question is, can you share config docs for the 9 techniques?
Yeah, they're primarily there in our docs.yugabyte.com/deploy/multi-DC. So if you go there, there are like various ways you can, touch on some of these techniques that I have highlighted. And we continue to enhance those docs. So if you don't see something, holler on Slack and we'll help you.
Okay, great. And Sid, we can include those links in the follow-up email as well.
Yes,
so
absolutely.
That everybody has access
yeah,
to
good
them.
point.
Okay. The next question, thank you for sharing the techniques. Can you describe in more detail how Yugabyte's database preserves Postgres compatibility while also being geo-distributed?
Yeah, excellent question. So Postgres is a very powerful grammar or the language around relational data modeling, right? And we have all come to love. It has been battle hardened over, I don't know, 20 plus years, minimum 20 years. So what we have been doing is taking that grammar and mapping into the geo-distributed, or first of all, distributed and then geo-distributed aspects of Yugabyte DB. So I'll give a concrete example. So we're currently working on, for example, row-level geo-partitioning. Now, the way row-level geo-partitioning is supposed to work, I explained. How do we map it to the Postgres construct? So we start with the Postgres construct of table partitioning. Now, what table partitioning in Postgres does is takes a big, I would say, parent table and allows you to slice that table into smaller, I would say, child tables. Remember, there is no foreign key relationship here. They're just child tables in the sense that each one has some part of the data. And in traditional Postgres, you're supposed to take those child tables and use things like table spaces, for example, to map them into different kinds of disks. So if you want the most latest incoming data to be stored on faster SSDs, then you'll map them. If you take slightly older data and you map them into hard drives, then you'll do that. So Postgres has tried to take the language constructs and obviously maps them to a single node, which is multiple disk potential architecture. What we have done is we're doing essentially the same thing, but now you can map them to multiple zones, multiple regions, multiple clouds, and without breaking the Postgres, I would say, the grammar constructs, right? So we can leverage its uniqueness and its richness of its language, and then exploit it when it comes to the distributed substrate that we have developed. Similarly, let's say follower reads. That's another great example, right? Now, traditional relational databases, follower reads is a non-existent concept because every read is strongly consistent by definition. It depends on what isolation level you're using, but they're still strongly consistent at the core of it. How do you bring that when the database is actually distributed and now there is a notion of a leader which has the strongly consistent data and the follower which has a timeline consistent data? So what we're doing is whenever you need to do follower reads, you change the session attribute of the driver that you're using and say that for the next set of calls that I'm going to make, I'm okay with follower reads. And that directive comes to the database cluster, Yugabyte DB cluster, and it knows that since it is operating in a session configuration where follower reads are allowed, it'll start serving follower reads. So we are, and this is just two examples I gave, almost every one of these techniques can be mapped to one of the Postgres syntax concepts, and we continue to enhance and I would say go deeper as we turn on more of the distributed nature of the database alive in the Postgres form factor. Okay. Any other questions, Michelle?
That is all the questions at this time. Thank you for joining today's webinar, and we'll see you at an upcoming Yugabyte event.